Hi, this video is about the difference between phase difference and also path difference for wave. Yeah. Okay. We look at this first. The difference between phase difference and path difference. Okay. For wave, then this one for wave you can apply to sound wave or electromagnetic wave, but I believe this one is more important in the electromagnetic wave, especially when you come to interference. Okay, now the phase difference, first one, okay, is the difference in the timing when the wave is wave started. Okay? For example, we have two waves, okay, moving in the same direction. Let's say to the right hand side. Okay, this is the direction of our positive x. Now let's assume you have a first wave started like this. Okay, sinusoidal wave. So this wave is moving in this direction with a group velocity v, and then I will assume that this one is our starting point. Okay, this one is a starting point. So this one is your wave number one. So I will call this one y1, and the second wave here, which is going to start a little bit later, will be called y2. So let's say after this wave, okay, move out, okay, and after one half of the cycle here, okay, after half of the cycle, then the second wave started to move out. Okay, so this one here. So what you see is there is a difference between the wave number one y1 and wave number two. So if they are moving at the same time, the difference between this one, it is called phase difference. Okay, so in this case, okay, phase difference here, okay, the phase difference here is normally the symbol we use is this one, phase difference or phase angle. This one is 180 degree. Okay, 180 degree. Now we look at the second phase difference, okay, of two waves that move out from the same location. Okay, y1 and this is y2. Let's say this is the first one. Okay, this is how the first wave looks like, and then the second one is, okay, here. Okay, it starts from here. So you can see the difference between them is this much. Okay, this one is 90 degree phase difference. Okay, so in this case, this one is 90 degree. Okay, 90 degree phase difference. So that's a phase difference. All right. Now the second one is the path difference. Okay, the path difference. Now when you talk about path difference, because it's the path is the distance covered by the wave, okay, but electromagnetic wave is not not easy to describe when you talk about wave motion, okay, because it involves a lot of other theory like Maxwell and so on. So our path difference here, to put it simple, is let's say we have two you have one light source. Okay, you have one light source. Okay, so let's say this is a light bulb. You allow the light bulb, okay, we need a guideline here. So you allow the light bulb to pass through one single slit, okay, one small opening. Now when you have this one small opening, okay, the light will pass through the opening, and then after that come to a second opening, okay, come to the second set. So this one is called single slit, and this one is called double slit. Slit are very small opening, okay, normally used for light, okay, experiment. Now we have here light, okay, shine on the first single slit, okay, and then because of diffraction, the light will be spread out with a larger angle, okay, at a larger angle. And then double slit, you got two slit again. So here you're going to have another diffraction, okay, another diffraction from the slit at the top and the slit at the bottom. Now, if you put a screen somewhere here, you're going to observe some sort of disturbance, okay, this area here, okay, this area here. So you're going to see something like a zebra crossing, okay, something like a zebra crossing along this area. This will be the bright one, dark, bright, dark, and so on. So the other side will be the same as well. Okay, so this whole process is called interference. Okay, this one is double slit interference, or Young's double slit interference, discovered by Young. Okay, so we call this one screen. Now, to talk about path difference is this. Why we have this bright area, bright, dark, and so on, or sometimes we call fringes. So this one will be bright fringe, and the dark one is called dark fringe. Okay, dark fringe. And then sometimes the word fringe is replaced by the word band. Okay, fringe, band can be interchangeably used in this type of explanation. Now, what is path difference actually? Now we come to this one. Okay, we draw this one and the screen here. Okay, this is our double slit. Okay, this is our double slit. Now, our double slit, we have two slits, which we are going to call this one S1 and S2. Slit 1, slit 2. And then your screen is at a distance away. Okay, this is a screen. Okay, and the screen, of course, you can see the result of the experiment, this area. Now, if you draw a center line that passes through the center of the double slit, okay, so the screen is 90 degrees and the slit is also 90 degrees from this reference line. Okay, now if you have you have a point somewhere at the center here, okay, or on this line, and if you draw a line from the slit 1 to slit 2, and if we call this point here point P, so that means S1 to P has the same distance as S2 to P. So if you minus them, S1P minus S2P, you get 0. So this condition we call the path difference is path difference, or the symbol we use normally is delta R, is equal to 0. Okay, some books they use this path difference, optical path difference. Okay, S1P is optical path. These are optical paths, optical paths. When you minus them, you get optical path difference. Okay, so that one is optical path difference. So that means when the wave coming from S1, S2 reach point P, both of them must be in phase. Okay, they will be in phase, right? They will be in phase. Assuming that the light coming from S1, S2 are coherent. Okay, they are coherent, right? Okay, so that is our first one. Now let's assume again, we use a different color, yeah, blue color. Let's assume we have a different point. We go to a higher point here. Yeah, a higher point that we call P prime. Okay, so if we draw two lines from S1 to P prime and S2 to P prime. Now we can realize that, of course, physically you see this thing, you know that the S2P prime is much longer than the S1P prime. So for the second one, this is our first one, yeah, red color. And then for the second one, we know that our delta R, which is equal to S2P prime minus S1P prime, this one is not equal to 0. So we say that the optical path difference is not equal to 0. Okay, so that one is the meaning of the path difference. Okay, why we use the optical path difference? Well, it's not the same as when we walk through distance, because for light, it's a bit different. Okay, for light is a bit different because they are made up of when we talk about wave theory, when we talk about wave theory for wave that passing through medium, they have something that can change. That is their wavelength. Okay, so when you talk about the path taken by light or electromagnetic wave, we normally use the optical path or optical path difference. Okay, we normally don't use the word distance. Okay, we don't use the word distance. Okay, so that is our explanation on phase difference and also path difference. All right, so I call this one page 1, and then the next one is what we call that diffraction grating. Okay, before you can understand diffraction grating, you need to know Young's double slit experiment. Okay, we start with Young double slit experiment. Okay, I think I will call this one number 1, this one number 2. Okay, this one number 2, this is number 1, number 2, and number 3 is called the Young's double slits experiment. Okay, so Young's double slit experiment is actually an experiment designed to measure indirectly the wavelength of light. Okay, so to measure wavelength of light directly is impossible, right? So what is Young double slit? This is Young double slit. Okay, so we gonna start using that same diagram. We need this guideline. Okay, we will do it physically here, draw it on a physical diagram, and then after that we do an analytical diagram. Okay, we have a light source. Okay, and then we have a single slit. The purpose of single slit is to reduce the glare actually. And then we have double slit. Okay, I will put the double slit here. Okay, this is my double slit. Okay, I put this one single slit, double slit. So this one is S1, this is S2, and a screen is here. Okay, and the screen is here. Okay, that is a screen. Now we know that the light will be diffracted. The light will be diffracted. Okay, so we draw the diffraction from S1, S2. Okay, another one is here, and then another one is here. So this is the angle of diffraction. Okay, so what is the next thing we need to do is I'm going to draw the wave front. Okay, the wave front. So let's start with some measurement is needed here. Okay, I'll use 1 cm for each of the drawing here. 1, 2, 3, 4, 5, 6, 7, 8. And the same thing also here. Okay, so I'm going to use a compass. We need a compass to draw the wavefront. Sorry, my color is black here. This one is a black. Okay, and then this one again. This is a wavefront. The maximum of the wave, normally we use a solid line to represent that. This one again. One more. Okay, one more, and one more, and then after that we draw the same thing for this one. Oop. Okay, this one more here. Next. One here, one more, this one. Okay, I think it's enough already. Now these are the wavefront. Okay, I should have used red color. So this wavefront here, as you know, it is made up of it actually represents the maximum. These are the maximum. The wave actually move up from S1 to the right, S2 to the right, become a circular wave. Okay, circular wave. So you have maximum, minimum, maximum, minimum, maximum, minimum. Same thing here, maximum, minimum. So if they spread out like that, sooner or later their energy will be spread out to a large area. So finally the wave disappear. Okay, but this if the condition is near enough, okay, around S1, S2, and then what happen is, when we look at this part here, this triangular part here, the wave from S1, the one that diffracted from S1 and the one that diffracted from S2, they will actually meet at this location. And when wave meets, there are two phenomena that will happen. When you have a maximum with a maximum run into each other, they will become a larger maximum. That one is called constructive interference. Okay. Another one is the minimum meet another minimum, it will become a deeper minimum. That one is also constructive. But wave have something that matter cannot be have, which is if you have a maximum of the wave and a minimum of the wave collide or meet each other at the same location, they will disappear. Okay, they actually disappear. It seems like they are not there. Okay, so that one is called destructive interference. All right. So this area, you see the one I use red dot. This area are places where maximum meet with maximum. So this is called constructive location, and this is called not. This is called what we call that, anti-knot. Okay, anti-knot. And then other than that, this area is also the minimum with a minimum. So this area is going to give you constructive interference. All right. So if we draw a line from the center here, go out, what happened on the screen now is that you're going to see bright band. Okay, you're going to see an area made out of bright band. So if you use a red color laser, you're going to see red band here. Okay, so next one, we look for other bright band. Other bright band is somewhere here. This is maximum with maximum, maximum, maximum. This area also, this area, this area, and this area. So if we draw that line roughly somewhere here, okay, so we're gonna get this area. So this area is also a bright band. Okay, bright band. And then the same thing happened to this location here, here, and here. So we draw a line from here. So we get another bright band, bright band, bright band. The bright band at the center is called the central bright band. Okay, the other will go in sequence. Okay, in sequence. All right. Now, those are constructive interference. Now we have another one is destructive. Okay, we have destructive here. So for destructive, we have this maximum and minimum. This is a maximum, minimum, maximum, minimum. So we use these 2 points to help us to guide to draw the line here. So this area is dark band. Same thing for this location. Okay, same thing for this location. There are actually more than that, more than 2. Yeah, so I just draw 2 to guide me. So what happened here is this area now is bright. This area is dark. This area is bright. So if you continue on like that, you have something called zebra crossing. So this is a bright band. Okay, this is a dark band. So I shade it is a dark band. This one bright, and then here is dark again, bright, and here is dark again. So they are actually mirror image. Okay, they are mirror image. So that is the Young experiment, Young double slit experiment. Okay, so we look at them mathematically. So we need to draw another one. So we look at them mathematically. So we start from here, double slit. For double slit, okay, and this is a center guideline, and that is a screen. Okay, that is a screen, and our screen here we have a different bright band and dark band. Okay, so the central bright, dark, and then bright, dark, bright. This one is dark, and then here is dark again. So let's assume the distance is L. Okay, And the distance between S1 and S2, this one is called D. Okay, this is D. So we choose a point here. We choose a point on the screen. First, we choose a bright band. Okay, the bright band. So we know that there is a distance like this, right? Then there is a distance here to here, and then S1 to this point. So I call this point P. Okay, this point is P. So S1, sorry, this is S2. S2, because P is above the horizontal line, so S2 is longer than the further from P compared to S1. So we have a data we write down here. So delta R is equal to S2P minus S1P. That's an optical path difference. Okay, and then we need to draw another line from the center. Okay, that's a 1. And then we're going to look at this triangle. So this line has an angle of theta. Okay, theta. And we draw another line which is 90 degree with this red line, but cutting through S1 here. Okay, this one is 90 degree. So the trick here is you need to use a little bit of mathematics here. If the angle theta is small enough, okay, small enough, then this one will become 90 degree as well. Okay, so we see here carefully. So when theta becomes smaller and smaller, this one is approaching, okay, here, this angle here, approaching 90 degree if theta is very, very small. Okay, if theta is very, very small. So when that happens, this angle here is also theta. Alright, so I will call this point here point N. Okay, point N. So we turn to the next page. We now look at two triangles here, or one more distance here. This distance is given by Y. Okay, the distance here is L, theta. And this one, this distance is D, and this distance here is delta R. Okay, this one is delta R. So we got triangle, two triangle to look at it. Okay, we got two triangle to look at it. Okay, page 2 here. So first triangle is the larger triangle. Okay, Y, theta, and L. So we know one thing, tangent theta is Y over L. Okay, we have one equation here already. Equation 1. And then we have another triangle, which is the S1, S2, this one which we assume already reaching 90 degree, right? Okay, this is theta, this is D, this is delta R. So now if you look at the triangle, we have sine theta is equal to delta R over D. Okay, delta R over D. Or your delta R is equal to D sine theta. So we have a second equation. Okay, which this delta R is also equal to the S2P minus S1P. Okay, S2P minus S1P. Okay, so why are we doing this? Okay, what we are supposed to do is actually put this thing in here, but there is a problem. We have sine theta and tangent theta, they don't talk to each other. But we know one thing mathematically is this. Okay, if theta is small enough, your tangent theta is actually the same as sine theta and also the same as theta. Of course, this one in the measurement of radian. Okay, measurement of radian. So we assume, okay, assume for small angle theta, okay, for small angle theta, our tangent theta is equivalent to sine theta. So that means our delta R is equal to D sine theta, but sine theta is equal to tangent theta, so our sine theta can actually become Y over L, or dy over L. Okay, dy over L. All right. Now, in wave, okay, in wave theory, okay, in wave theory, according to superposition principle. Okay, superposition principle. Number one, to get constructive interference. Okay, our delta R must equal to either 0 or 1 lambda or 2 lambda or m lambda, where your m, okay, or any lambda that represent an integer number, okay, or we just put just put it like that, okay, 0, 1, 2 and so on, okay, or we generally can put m lambda where m is equal to 0, 1, 2, 3 and so on, okay. So that means we have two equations of delta R now. One is this, another one is this one. So we have dy over L is equal to m lambda. So our y is m lambda L over d. So this is the equation used to calculate the brightband distance. So this is equation number 3 now. Okay, and same thing happen to the destructive. Okay, and according to the superposition principle, to get destructive interference, okay, to get destructive interference, our delta R must equal to half lambda, 1.5 lambda, 2.5 lambda and so on. Or we can have 0 plus half lambda, 1 plus half lambda, 2 plus half lambda and so on. So here generally we can actually replace the 0, 1, 2, 3 and so on with m. So now we have this lambda where m is again the same, 1, 2, 3 and so on. So thus now we have the second equation, which is your dy over L is equal to m plus half lambda, or your y is equal to m plus half lambda L over d. So that's the equation for the dark band. Okay, the equation for the dark band, where the m, okay, is called the order number. Okay, the order number of the experiment or the interference. Okay, so this one is Young double slits. It only got 2 slits. There are problems with Young double slit. The problem is because you only got 2 slits, so the image is not really that bright. You have to observe it in a dark room. Okay, so to solve that problem, okay, to make the image have a better contrast or brighter, we normally use more slits. Okay, so how do you make slit like that? Of course, that one is under what we call that. This is the third one already, or this is the fourth one. This is under the what we call that, diffraction grating. Okay, diffraction grating. Now, what is diffraction grating? Well, simply put, diffraction grating is a lot of these lines, slits made on a piece of plastic transparent material, or the best is a glass. Okay, how do you do it? Normally, how do you do it is we put some liquid, okay, some gigantic molecule liquid, normally like solvent, okay, organic solvent, and then when you put organic solvent, what happens is this molecule, they are in random direction. They're in random direction, so it does not help us in doing experiment for wave. But if we put very strong, okay, if we put a very strong electric field between them, then it might help. Okay, so what happens if you put them between two very strong high voltage parallel plate? Okay, you apply them to very high voltage, positive and negative, you are producing very strong electric field between them, right? So what happens with this electric field? Molecule will line up. Okay, molecule will line up. Okay, and since molecules are small, the line they make will be extremely close to each other. Okay, so they will line up like that. But when you let go of the voltage, so this line will, because of thermal heat from the surrounding, they go back to something like this. So you need to fix this thing. Okay, we need to fix the line. So what you do is the liquid here, yeah, the liquid or the liquid solvent, the organic solvent that we have, normally we actually mix them with some sort of a UV activated type of epoxy. So that epoxy will become hardened, or the glue will become hardened when you expose them to UV light. So what happens next is, after you line them up using electric field, you expose them to UV light, and the epoxy will be hardened and trap the molecule in that pattern. So even if you take out, okay, even if you take out the voltage from the parallel plate, so now you will have molecular structure that line up perfectly straight, okay, relative to each other, and they are very close to each other. And that one, they can actually behave like Young double slit, but in a, what we call that, in a turbo scale. Okay, in a turbo scale, much more powerful, and more light can pass through and give you better contrast. Okay, so that is diffraction grating. Now diffraction grating come with something new compared to, relative to that Young double slit. The distance between them, okay, you have something called the number of line. Okay, number of line per meter or per unit length. So that one is called N. This one is how many this line, okay, per unit meter. Okay, so that one actually give us a rough estimate of how far the distance between them. So that one is called D, the line, the distance between the line. Okay, so that D is roughly equal to 1 over N. So you have to remember this equation. Yeah, this equation number 5. Okay, so we have this diffraction grating. So diffraction grating experiment is the same as our what we call it, Young double slit. The only difference is it has a better contrast, brighter result. Okay, brighter result. Okay, brighter result. Now we look at the equation for our next part here. This is page number 3. So our equation will be same. Okay, for bright, okay, for bright fringe, okay, you have this equation, right? You see, you have y is equal to m lambda L over d, but your d is equal to 1 over n, right? So it become n m lambda L. So now we have another equation which is used for diffraction grating. So that one I will call equation number 6. And then for our dark fringe, your y is equal to m plus half lambda L over d, and which is equal to n m plus half lambda L. Okay, so that is a difference between Young double slit equation and diffraction grating. Okay, so I hope this one will clear your question on those 3 concepts: your diffraction grating, your phase difference, and your path difference.